All right, good morning, everybody. Welcome to session SPF303. Can I get a quick show of hands? How many of you watched NASCAR races on Prime Video? All right, great. We've got some NASCAR fans in the room today. My name is Arvind. I'm a senior solution developer in the prototyping and customer engineering team. With me, I have...
Hello, everyone. I am Mona. I am solution prototyper, also from prototyping team.
We are super excited to take you through this journey of innovation on real-time film analytics and how we actually brought it to millions of NASCAR fans. So on the agenda today, we're going to have a brief touch on the NASCAR coverage on Prime Video. We'll understand more about the burn bar innovation. For most of the session today, we're going to spend some time on understanding the solutioning aspects. And then I'll wrap it up with a call to action, which I hope will inspire you to build solutions in your organizations, which are very similar to what we've done here as well. So I want you to imagine this. You're watching a NASCAR race, and you see two racers fight it out for a position. One of them is charging really hard, while the other is holding back. And as a fan, you wonder, why is this driver really holding back? Is it a problem in the skills? Is there a problem in the car? Or is this racer actually playing a much longer game of fuel strategy so that he wants to position himself to be a leader at the end of the race? So fuel strategy is something which has never been made visible to both broadcasters and fans. But if you think about it, fuel strategy still remains one of the most critical and exciting parts of a NASCAR race. So we challenged ourselves and said, how can we use the concept of a fuel strategy to unlock unique storytelling opportunities and equip our on-air talent so that now they can drive fan engagement by providing deep technical insights to what the racers are really doing on the track? The key challenge here is this is a race, right? And fuel strategy keeps changing very, very often, every few seconds, perhaps, in some of the races. So we want to make sure that these fuel insights are provided to on-air talent in a near real-time basis. So we chose an option where we said we want to actually equip our on-air talent to have this fuel insights in less than 5 seconds. So this was a primary challenge for us. So what we did was we built the burn bar. So what is the burn bar? It is truly an industry-first innovation from the Prime Video innovation team, which basically gives us an ability to look at a driver's pattern. What is the strategy on their driving? Are they driving really aggressively? Are they driving conservatively? What's the fuel efficiency they're getting out of their cars? There are two aspects to the burn bar. We actually created a customer-facing graphics, which is displayed during the broadcast, which is an example that you see on the screen. And what you don't see is a real-time dashboard, which is actually made available to the on-air talent. Now, this real-time dashboard is critical because this is what enables our on-air talent to be proactive rather than being reactive. They're able to spot fuel strategies as they develop during the race before any of that becomes obvious for the viewers. So this combination of the customer-facing graphics and the on-air talent dashboard is really powerful because we're not just showing some data, we're actually equipping the on-air talent to develop interesting stories and engage the fans as they watch these races. So for those of you who haven't seen what a Burma really looks like, let's take a look at it.
And trying not to allow that 11 car to get by.
Well, let's check it out. Chase Briscoe getting nearly 5 miles a gallon. Denny Hamlin 4.6, meaning for every gallon of gas, Chase Briscoe's going about another third of a mile, another quarter of a mile. That over the entire fuel run may be a difference. So to your point, that's not by luck and that's not by tune-up. That is Chase Briscoe saving gas versus Denny Hamlin. Fuel mileage continues to play a role here at Pocono.
Right here at the end of the straightaway. He's probably lifting a little bit there, and that jumps up to 5.2.
Look at that, last lap, big saving, big chunk of saving right there.
And it allows...
No braking to one or left brake, just drive in deeper. That partial lift is not doing it for us.
So what you saw just there is an example of how a burn bar actually looks like and how it's been used by the on-air talent to actually engage the fans as the race occurs. Now, the Pocono race here was very intriguing because it's one of those races where fuel strategy played a vital role for Chase Briscoe to actually win it. Now, if you analyze this race, he actually had a really nice fuel-saving strategy where he was basically lifting off the throttle at the beginning of the straights and coasting at the turns. So if you really haven't watched this race, I highly encourage you to take a look at that. Now, let's look at some of the challenges that we had to go through to build this capability. The first one is the lack of real-time fuel data that our on-air talent can make use of to actually provide strategic insights. We wanted to actually create a really engaging customer broadcast. Now, this is a race. We deal with thousands of telemetry signals that are coming from each of these NASCAR cars. And we wanted to actually process all of these telemetry signals in real time in a much reliable and a highly accurate way. Now, I know some of you who may not be aware of NASCAR racing might be wondering, why are we even talking about things like fuel consumption, fuel efficiency? Isn't it all straightforward? I mean, all the cars have it, isn't it? Some sensors or gauges. Not in the case of NASCAR cars. None of these cars have any fuel gauges in them. None of them have any sensors which give us any indication about fuel efficiency, fuel burn, any of that. Another interesting challenge here is fuel strategy still remains one of the most guarded secrets in the NASCAR teams. Each of these NASCAR teams own this secret. It is competitive intelligence at play here. So there's really no way for us as a development team to reach out to them and say, hey, can you share any of your strategies with us? Finally, the lack of ground truth data. Now, obviously, you will see that we've got some machine learning models as well, but the lack of ground truth data really makes it hard for us to actually train a model and integrate it into the processing system. On top of it, there are too many variables which actually impact fuel consumption and fuel efficiency. These variables could be, for example, driving styles. It could be track temperatures, weather conditions, and a whole lot more. So, having seen these challenges, let's look at some of the goals that we actually set for ourselves here. The first was to determine the fuel analytics. We want to figure out how much fuel is being burned in the current lap, in the last few laps, across stages, and provide trends to the on-air talent so they're able to spot these fuel strategies as they're developing during the race. Next, the Prime Video innovation team have really stringent KPIs, both in terms of performance and accuracy. So this solution had to meet all of that. We had to provide these fuel insights to on-air talent in less than 5 seconds. We want to enable broadcasters the ability to display this burn bar graphic on demand. And finally, create a real-time dashboard for the on-air talent. So for the rest of the session today, we're going to look at details about how we build the solution. So I'm going to begin with a really high-level architecture of what's involved in the system. The first thing I want you to look at is we've only relied on serverless and managed services from AWS. We are an extremely small team, and we didn't want to really spend a lot of our time looking at the operational overhead or managing servers. So we said, from day one, we're going to adopt these serverless technologies and manage services from AWS. I'm going to kind of quickly walk you through a data flow here. Telemetry signals from these race cars basically flow into ERDP. ERDP happens to be NASCAR's data distribution official platform. All of that data is now ingested into AWS. Now you'll see that we've got different layers. These are all separation of concerns. The first layer is the data ingestion, where we use AWS Fargate along with Amazon Kinesis data streams. Once we've got all of this data flowing into Kinesis data stream shards, we use the processing layer where we actually make use of Amazon Managed Service for Apache Flink. So Flink happens to be the core processing engine for the entire solution here. Flink integrates with the AI layer, where Mona is going to talk about some of the models that we've developed and how we integrate that with Flink. And finally, once we've determined some of these fuel analytics and trends, we persist all of that into the storage layer, which is later distributed to broadcasters and to on-air talent dashboards using API Gateway and delivered over Amazon CloudFront, where we also make use of AWS AppSync. So what we're going to do in the next remainder of the session is go through every layer and understand each of them in depth. But first, I'm going to call on Mona to talk about the work that we've done on fuel analytics.
Thank you, Arvind. As Arvind explained, one of our biggest challenges was we had no direct information about how much fuel left in each car. No car broadcast, I have 5 gallons left in the middle of the race. So we watched hours of NASCAR coverage. We consulted with subject expert matters from Prime Video Innovation Team to learn about fuel analysis, race analysis, and also the physics of fuel consumption. So from day one, we knew that no single approach would crack this problem. So we took 3 different approaches. The first one was vision analysis or computer vision. There are several fuel consumption and fuel consumption that we can extract from NASCAR video coverage by training a specialized computer vision model. We analyze different behavior like drafting, pack racing, and so on, that they have correlation with fuel consumption. The next approach was physics-based model. Physics-based model are parametric model that maps the set of telemetry data point to fuel consumption. And to find the parameter of this model, we use historic races with different characteristics. And also we use real-world events such as green flag, yellow flag as calibration point to optimize the parameter of this model. Once we build our foundation, we use Amazon SageMaker to train an AI specialized predictive model to calculate fuel consumption. Unlike the previous approach where it was like parametric model, this was data-driven, allowing the model to find pattern and correlation in the data. The result of this exercise, or like all this experiment, we settled down on 2 approaches: the physics-based model and machine learning model. Now let's see how we deploy this model and use it in our solution. The AI-based model lives on Amazon SageMaker inference endpoint that's capable of like running computationally intensive inference prediction. The SageMaker gives us auto-scaling, which is so critical when we are processing 40 plus cars during the race. So we automatically is able to do the auto-scale during the inference. Also, we are talking about like millisecond inference time using SageMaker inference endpoint, which is critical when we want insight every 5 seconds. So then our physics-based model, we embed that in our real-time processing layer, where Arvind explained more about like this layer. So now that we talk about how we train the model and also where we deploy the model, let's learn about the data. NASCAR next-gen cars transmit thousands of telemetry data every second. This can be throttle position, RPM, brake pressure, and so on. This data flows into a NASCAR event data racing platform, or ERDP. This is how broadcaster racing teams and other authorized entities subscribe to access the data. ERDP uses NATS, which is a messaging system that enables pub/sub for real-time string. This is particularly good when we are working with and this gives us the high performance and low latency. So now Arvind is going to talk about in detail about the AWS architecture that we use to ingest the data from ERDP using NATS. Thank you.
All right. All right, thanks, Mona. So now that we've got telemetry signals coming into the ERDP platform, let's understand how we ingest all of that data into AWS. So you will see here that the first thing we are doing is running subscribers. We've got subscribers which subscribe to this ERDP data using a single ERDP endpoint. These subscribers are essentially ECS forget tasks which run in multiple AZs. More importantly, because we use NATS, which is enabled by ERDP, which is what ERDP supports, we also make sure that these tasks share the same NATS queue group, which actually gives us two important capabilities. With NATS queue groups, NATS will ensure that it actually is able to load balance messages as they arrive to multiple subscribers, which are actually running in multiple AZs. Now, NATS also will ensure that it will deliver a message only once to a single subscriber in this group. Now, if one of those subscribers were to become unhealthy, NATS will ensure that it will load balance it. It will push those messages to the healthiest subscribers. And that's basically the fault tolerance aspect that we get out of it. Now that we've handled all of those aspects, the next thing we do is we route all of those incoming data into multiple Kinesis data streams. Now, one thing we don't have here is we don't really have an exhaustive list of all the telemetry signals that are being used. But you want to imagine that there are plenty of signals that we get. And so we basically separate out these signals logically to be sent to multiple Kinesis data streams. I want to quickly talk about some best practices for stream consumers here. Now, if you step back and look at what these subscribers are doing, they're essentially subscribing to the ERDP endpoint, get all those messages, and route it back to multiple Kinesis data streams. So if you think about what the subscriber's role here, it's more like a pass-through layer with very little processing happening. So we want to make sure that we maximize the throughput for each of these subscribers. So from that aspect, you want to make sure that every implementation that you're doing within subscriber is asynchronous in nature. You don't want any blocking networking calls. So one of the things we also do within the subscriber is, for example, publish a lot of custom metrics for monitoring. For monitoring, for example, the latency, the throughput, etc. So we don't want any of those blocking calls, so we obviously want to rely on a lot of asynchronous calls there. The next thing we do is monitor for back pressure. This is a critical aspect for many of the streaming systems because this is essentially a problem that occurs when you have a lot of messages that arrive really quicker than what a subscriber can process. And it gets manifested in two different ways. First is memory exhaustion, where you have messages that land, they get accumulated within a queue, and thereby your queue depth keeps increasing. The second is a message loss, where you typically run into buffer overruns. So you want to make sure you can use CloudWatch with alerting, which is kind of what we use, and we set up alerts to monitor all of these aspects. The other thing we also want to monitor is the throughput and the latency that we are seeing. As I said, the subscriber has to be extremely efficient so that we are not causing any more latency with the overarching goal of saying we want to actually provide insights every 5 seconds. Another really critical aspect when it comes to stream processing is you have to question yourself this. Do you need every message that is coming through the pipe? Every message, do you need to really process it? Do you really need it? If not, you want to actually use something called as adaptive sampling. Now, there are cases where, for example, you will require every message to be processed. In our case, if you think about we receiving thousands of telemetry signals per second, if I get thousands of telemetry data points in every second, which is corresponding to, let's say, engine speed, do I really need so much data points? Absolutely not, right? So when we did that analysis, we see that there is really no need for us to process every single message. So what we do instead is we have some sophisticated adaptive sampling strategies in place. And that really helps us because now all of a sudden we don't really have to now scale the processing layer to some crazy levels that is really not required for what we want to do. Now that we have the data ingested and stored durably within Kinesis data stream shards, let's look at what and how we actually process all of these real-time data streams. First, I want to actually start off with some core requirements on why we pick the Amazon managed service for Apache Flink. We wanted a service which can give us the ability to process stateful computation for both bounded and unbounded data streams. We want the ability to connect to multiple data stores with really nice state management capabilities built in. And additionally, but more importantly for our specific use case, we wanted a service which can help us convert unbounded data streams into bounded data chunks. We call it windowing, is a concept that's present within Apache Flink. We'll get into those details very soon. So that brings us to Amazon Managed Service for Apache Flink. So it is a managed service, perhaps the easiest way for you to actually start building analytical applications when it comes to real-time data streams. You have the ability to run these Flink applications on a continuous basis. It supports both bounded and bounded data streams. A great way of getting started with Apache Flink is to make use of Zeppelin notebooks. With Zeppelin, you're able to analyze these data streams in an on-demand way without even having to create an Apache Flink application. You could write, for example, you could use a SQL way of interaction. And for example, you want to figure out if there are anomalies in the real-time data you're getting, or you want to create some visualizations, or you want to perform some data analysis. You're able to do that on the fly using Zeppelin notebooks. And the Apache Flink service supports that. Finally, the service actually supports you to build application in multiple programming languages. So where does really Flink fit in the overall data streaming services that AWS provides? So on the left, we've got different sources for real-time data streams. In the ingestion and storage layer, we offer two capabilities or services, Amazon Kinesis data streams and managed streaming for Apache Kafka. In our solution, we made use of Kinesis data streams. Once we've got this ingestion covered, we can use the Amazon managed service for Apache Flink to process all of these real-time data streams. And then with Flink, you have the opportunity to now send all of this processed data to multiple destinations using the concept of Flink syncs. Let's come back to our solution and look at the concept of a Flink pipeline. What does it really mean? So at a high level, what this really is essentially a data processing pipeline. So in our context, we're dealing with multiple Kinesis data streams. We'll build a pipeline within Flink using some of the constructs that Flink offers. There's a really nice integration with Kinesis data streams. And then we also use the concept of a broadcast stream, and we'll get to the concept and what it really means in the next few slides. Then we actually use enrichers to add additional context to the stream that is flowing into Apache Flink. Finally, if you look at one of our goals was to actually provide these insights to the on-air talent every 5 seconds. So we are dealing with a case where we have unbounded data streams coming in, but our requirement is to actually provide insights every 5 seconds. So we really don't have to process all of those streams in an unbounded fashion. Rather, what we could do is we could use windowing options within Flink to break it down into more of a batch process, right? So this is exactly what the tumbling window actually provides us, and we'll get into what tumbling windows means. So a lot of the fuel analytics work and the processing that we do, including integration with the AI models, happens within this windowing functions. Once Flink processes all of those data points, we've got the fuel analytics in place, we flush all of that data out to an output Kinesis data stream, which is further consumed by downstream components. Next, we'll walk you through a couple of really key important concepts within Flink, which is what is really important for you to build processing of real-time data streams. The first is the concept of a keyed stream. So Apache Flink is a distributed system. So when you start sending data streams to Apache Flink, you have the ability to actually partition this data stream and run it in multiple task instances. How you partition the data stream is actually done using something called as keyed streams. An example is being shown here, using which we are basically we use the key by operator. If you look at the enriched data, that is the enriched data stream, which has all the enrichments in it. Then we use the key by operator. We use the vehicle ID in this case, and let Flink partition it out. And what that does is Flink will now partition the stream and make sure that all of these partitions are being processed on each of these tasks. These are, on the diagram, you will see that we've got events coming in for 3 different vehicles, and Flink has partitioned it and is basically running each of those partitions on different task managers in parallel. So when we talk about low latency, high throughput processing capabilities on Apache Flink, this is exactly what we mean. So if you really want higher throughput, you have an option to now horizontally scale it and run it on multiple task managers and task instances. Now let's get into the concept of a broadcast stream. Broadcast streams are really powerful in that you're always going to have cases where you've got your real-time data streams being processed by an existing Apache Flink application. And you actually have specific events that occur very rarely. In our case, very rarely in a race. For example, maybe there is a car crash that happens in a race. There are also events where racers have to pit stop. Now, if you think about some of these events, these are events that don't occur on a continuous basis. So you're always going to have a main data stream, and then you're going to have the sporadic data streams as well. But you want your Flink app to make use of these events, these short-lived events, as they occur. So the way you're going to enable that is using the concept of broadcast streams. So with broadcast streams, you have an ability to distribute your reference data to all the parallel instances, and they can process them in parallel. And one of the things you can also look at here is how you want to make sure that these data is available for all of those task instances that are processing your real-time data streams. And in those process functions that you're writing, you're able to now tap into these broadcast streams and pick up the state changes and incorporate that into your logic. Next, let's talk about the tumbling windows. This goes back to the goal that we want to actually provide insights every 5 seconds. So we break down this unbounded data stream into bounded chunks using the concept of windows. Now, in our case, we use the concept of tumbling windows, and we do that on purpose because we don't want any overlapping between those windows. We want to make sure that events are exclusively falling into specific isolated time buckets. So with tumbling windows, you get non-overlapping, fixed-size time buckets. And in the example here, you see we've got 3 different windows with a window size of 3 seconds. And you'll see that each of these events have been placed in each of those windows. And there's absolutely no overlap. By far, the most powerful concept within Windows is process functions. So what happens with Flink is after 3 seconds, if you look at the window 1, after 3 seconds, Flink will close this window and invoke the process function. And this is where you perform all the analytics that you actually want to do with all of those events that have been aggregated into that time bucket. Another important concept to understand here is you're going to be dealing with a lot of state within Flink. So one thing you want to understand here is if you're not managing state the right way within Flink, Flink is going to actually remove all of that state when it closes that window. We're going to talk about how we persist this state across windows next, using something called as keyed state. Keyed state lets you persist state across windows within Flink. So if you look at our example, if I want to know at any point in time, hey, tell me this vehicle, tell me how much fuel has it burned till now in the current lap. It's like a running total that I want to maintain. And because I have this 3-second windows, I want to make sure that I'm aggregating across all of these windows. And that's state for me. So I want to persist this across windows. And the way I do that is by using Flink primitives, such as value state and map state. Flink actually supports a lot more, but we're actually using value state and map state in our solution. The other cool thing about this is also it enables fault tolerance and state recovery using the concept of checkpoints within Flink. we'll talk about checkpoints very soon. Now, as with anything, whenever you're dealing with state, you always have to think about how much of state am I actually aggregating on my side? How much state is being collected? So an important consideration is to think about state size. So what do you do with it? If you don't really handle state in the sense that you want to actually try and clean up unwanted state, you're going to have some resource contention issues here, right? Perhaps you're going to get into unbounded memory growth and have problems with availability and so on. So what you want to do is think about what makes sense for your applications. Think about different ways in which you can actually clean up the state. Flink allows us multiple options. There's the time to live, state TTL, which Flink automatically handles. It'll expire this state as long as there is no activity in it. Then you also have programmatic way of cleaning up the state. Finally, you also have a timer-based where you actually register callbacks, and Flink will call it on your behalf. Now let's talk about checkpoints, which actually gives us a really important capability, especially when you're running systems continuously to process unbounded and bounded data streams. This is the concept of checkpoints. What checkpoints allow you to do is to take a consistent backup of your application state across all Flink operators. So if you look at the example here, if you look at the data stream that we have, we've got multiple events coming in, and Flink service can actually initiate a checkpoint in predefined intervals. This is a configuration that you can have within the service, and the Flink service will make sure that it's actually checkpointing this state. It does so by storing all of this state in Amazon S3. And when Flink sees that there's a problem with one of the operators or the underlying task instances, it initiates a restoration from the previous successful checkpoint. So when you're thinking about this, you want to make sure that the state that you're persistent within Flink is really optimal. You want to monitor for checkpoint duration. You want to monitor for checkpoint sizes. And the way you do that is by, again, you can have custom metrics, using CloudWatch. And once you see, if you're seeing some of these checkpoint durations or sizes looking abnormal, it's a pretty good indication that your Flink application state is really high. And it's time for you to really optimize that. Another important aspect when you deal with real-time streams is messages getting out of order. In a distributed system, it is bound to happen. You're going to have messages which will get out of order sometimes. So as a solution provider, you want to think about, what does this really mean to my system? If I have messages coming in real time, but all of a sudden I've got some messages which come 10 seconds out, do I still process those messages, or do I simply ignore it? This is a decision that you really have to take as a development team. This is where the concept of watermarks is applicable within Flink. So with watermarks, you're essentially telling Flink that events up to time t has arrived. And when Flink sees that, it basically closes the window and triggers the process function. So in this example, what we're showing you is a setup where we have a window size configured as 3 seconds. However, we are also telling Flink that you can expect some events to come out 10 seconds out from now. Right? So basically now, Flink, instead of closing the window in the first 3 seconds, it's going to actually wait for 13 seconds before closing that window. So this is a trade-off between latency and accuracy. Whether you want to actually process every message, even though some of those messages are delayed, or is it okay for you to drop the delayed messages with the gain that you're getting in terms of latency? So coming back to our use case, we want to actually create insights in less than 5 seconds. So if I have a message which is beyond 5 seconds, we essentially drop it. Right? So this is a conscious decision that our team took. And I encourage you to kind of revisit this concept when you start developing your systems as well. So when you're building such a system, you obviously want to look at observability, which is very critical. You can obviously use a lot of CloudWatch metrics that is available out of the box. But when you're working with Apache Flink, it is bound to have, you're going to be creating a lot of custom metrics as well. A great way of implementing that is by creating custom sinks within Apache Flink. With custom sinks, you have the liberty to encapsulate all of these API calls. You can batch them up for cost optimization. You can handle any throttling errors, if at all you're subjected to, by implementing some retry logic, using exponential backoff, or you could even implement circuit breakers as well. Right? Think about encapsulating that into custom sinks within Apache Flink. Next, I want to talk about various options for you to optimize on the throughput. And I'm going to focus on 3 important services in our solution. Starting with Kinesis data streams. The way you increase throughput and scale Kinesis data streams is using the capacity mode that the service provides. There are 3 different capacity modes that we support. The first one is the provisioned capacity mode. This is applicable for use cases where you have a predictable data stream, you know how much throughput you will require, or you have a steady increase in the input data stream traffic. That way, you are able to now configure the number of shards you want to actually enable within Kinesis data streams. The next option is the on-demand standard. And you want to actually use this option where you have unpredictable behavior or unpredictable traffic patterns. You may expect sudden surge in the traffic pattern as well. And that's the place you want to actually make use of on-demand standard. The only thing you want to be careful with the on-demand or watch out with on-demand standard is when you have extremely high surges in data stream traffic, you have to know that the producers may be subjected to throttling. Now, we very recently announced the third option, which is the on-demand advantage option. With this, you really get a combination of nice performance with cost optimization. You want to use this option, again, when you have unpredictable traffic patterns. But the distinguishing part between the advantage and the standard is with advantage, what you do is you essentially provision warm throughput. So you could say, for example, I want my Kinesis data stream to have a warm throughput of 100 megabytes per second. And if your traffic looks like, maybe it starts with 5 megs per second, and then all of a sudden you're seeing 50 megs per second, and all of a sudden you're seeing 85 megs per second. This is going to be instant scaling. Kinesis will handle this ingestion without any problems because you've already warmed the throughput, right? So if you haven't checked this option, I encourage you to definitely take a look at it. The next service to think about in terms of throughput optimization is Apache Flink. And your option here is to make use of parallelism and something called as KPUs. So you want to think with Kinesis, with Apache Flink, your option to scale out is by increasing the parallelism, and you could further break out those parallelism into something called as KPUs, and you're essentially billed for the number of KPUs you're provisioning. So it's a great option for you to think about, one, optimizing the Flink pipeline that you've developed, and two, how do you actually optimize the throughput by provisioning the right amount of parallelism and KPUs. Finally, I want to talk about SageMaker AI inference as well. So with SageMaker inference, auto-scaling is a great option. It's an option that we actually currently use as well in our solution. There are, again, different techniques for you to actually establish this auto-scaling. As Mona called out, if you are interested in low latency inference timings and you want to be able to scale out as the demand rises, auto-scaling is the way to go. Now that we've seen some details about what we do within Apache Flink, let's look at the next architectural area, which is about how do we enable these live dashboards for on-air talent. So if you recall, one of the steps within the Flink workflow is once we figured out all the fuel analytics, we push out all of that data into an output Kinesis data stream. From that data stream, we use AWS Lambda functions to actually consume all of that data from Kinesis data stream, push it out into the storage layer, and which is delivered to the dashboard as well as partners using API gateway. So in our design, we actually use a single table design within DynamoDB, and we make use of AppSync, AWS AppSync, for GraphQL capabilities. So what is AppSync here? So if you think about traditional APIs, there are a lot of complexities in it. One of the biggest complexity is underfetching and overfetching. So if you've ever created RESTful services, RESTful APIs, you will see that in some cases, clients get a lot more data than what they expect. In some cases, clients actually get lesser data than what they expect, in which case, clients end up making multiple API calls to get the right information that they need. The other thing you also want to think about is, what about real-time APIs? If you want to enable pub-sub mechanisms for APIs, how do you do that? Right? So there is some complexity out there, and which is where these are the kind of complexity that AWS AppSync service solves for us using GraphQL. GraphQL is a query language. It is a strongly typed query language, which lets clients now create data structures to make calls to get the right amount of information from each of these APIs. This is a serverless managed offering from AWS, and it makes it really easy for you to actually build highly scalable pub-sub mechanisms for APIs and for websites as well. So how do we use this in our solution? So the Lambda function, which is used as a trigger to the output Kinesis data stream, reads the data from the Kinesis shards, and it initiates a mutation on the AWS AppSync service. We've already registered DynamoDB resolvers with the AppSync service. Once these resolvers are in place, AppSync automatically pushes that new data that we got from the Kinesis data streams into the DynamoDB table. Now, once we persist this state in the DynamoDB table, using a concept called GraphQL subscriptions, AppSync now delivers all of this data back to the connected clients. So in our example, these are custom React front-end web applications which use GraphQL subscriptions to connect to the AWS AppSync service. Once they connect, AppSync establishes a secure WebSocket connection with these clients. And once the mutation happens on the AppSync side, it uses a resolver, pushes data into DynamoDB, and broadcasts all of that data back to the connected clients using WebSockets. So let's look at what we've been able to achieve. What kind of results have we seen with this solution? So we launched the burn bar for the very first race, which was broadcast on Prime Video. This was the Coca-Cola 600. This was the very first time where field strategy was really publicly made visible to any broadcaster. And the reviews and the positive feedback has been amazing. A lot of media attention as well. We've landed about 534 million impressions on all of these articles published on various media outlets. NASCAR and Prime averaged more than 2 million viewers. More importantly, what we've done here is we've actually created a foundation on which we can actually further build additional capabilities and features upon. Finally, going back to the success criteria we had, where we wanted to actually provide fuel analytics, meet stringent KPIs, we've been able to meet all of that. So how did we really get to this solution? It was really not luck. We've actually made use of the AWS well-architected framework. This is a framework which actually gives you a set of best practices around different pillars. So if you haven't really checked out the well-architected framework, I highly encourage you to take a look at it. This is our very first iteration of this solution. While we've been very successful in meeting the business objectives, we know there are opportunities for us to improve upon in the solution as well. And we will use this framework as a guiding principle for us to actually get there. For those of you who are interested in this, we do have a well-architected framework tool, which is a self-service tool that you can actually use to perform reviews on your own. You could also reach out to your account teams or account SAs and see and to get their help if you're interested in getting some of your workloads reviewed as well using this framework. I want to next talk about call to action here. So if you look at some of the challenges, this was really an area where we were completely new. So this is we getting into uncharted paths. You want to actually embrace failure here, right? The biggest risk is not about taking an uncharted path and failing, but rather being on a paved road while others take it. So definitely be open to taking this uncharted paths, embrace failure. When you've been doing experiments, look at how you can scale them as well. Because scaling is where the actual real value lives, right? So you want to definitely make sure you're scaling. And you want to be receptive to two-way door decisions as well. Because this is, in many ways, when you're innovating, you are going to hit some problems. But you have to have a detour that you want to be able to take and take a different door and different approach to be successful. Finally, empower teams to accelerate the experimentation velocity. AWS gives you a lot of services and tools for you to do that. We do have a few blogs that I highly recommend you to take a look at if you're interested to understand how NASCAR sends all of that data, telemetry signals into ERDP. Definitely, there's a really nice blog that you can actually look at. Feel free to take a look at some of the driver testimonials and press releases that we have on the burn bar innovation. Quick show of hands, what do you think is the effort we took on building the solution? Any takers? How long do you think we took to build the solution? Six months? We had an MVP in 8 weeks. We already had, we started some of the integration testing with real racing data in 8 weeks. In about 12 weeks, we had productionized the system with a small team. So me and Mona are going to be sticking around. If you have additional questions, please reach out to us. We'll be here. Thank you so much for your time. Have a great conference, everybody. Thank you.